Okay, hello everyone. Welcome to our second recorded lecture of the week. So today we will be continuing our discussion on logistic classifiers, and if everything goes according to plan, we'll wrap up this section on logistic models today. And then in Friday's lecture, we should hopefully start on neural networks, which are a very exciting topic. So I'm looking forward to getting to those. So just a couple of really brief announcements. Again, no in-person lectures this week. So, of course, if you're watching this, hopefully you didn't show up to the lecture hall today. Friday's lecture will also be recorded and posted to Canvas in the same way that today's is, so keep an eye out for that. But we'll resume with in-person lectures as usual on next Monday, so please do show up to those in person. Your attendance is appreciated. And then the only other announcement today is that the second homework is due on Friday at midnight. So again, as always, please make sure to be using the Ed board if you have any questions regarding this homework, and make sure you are using the TA office hours as well to get some help on that assignment if you need it. Okay, so in today's lecture, we're first going to do a brief review of logistic models. So kind of, summarizing what we had already said about these, just kind of getting everything into one place all at the same time. After that, we're going to see a calculation for how you actually get the gradient for these models. So we're going to be fitting these models using gradient descent. So of course, we need some expression for that gradient. We'll also see some sort of additional advanced topics about logistic classifiers. And at the very end, we'll see some extensions beyond what we've already done. Okay, so the story so far, what we've said about logistic models, is that we're trying to predict some binary label y from some feature vector x. So we're doing binary classification here. And in a logistic model, what we're really doing is modeling these conditional probabilities, p of y equals 1, given our data point x. So we're interested in what is the likelihood or what is the probability of the corresponding label for this data point being y equals 1. Okay, take a second to just pause and think about why we don't need to model the other class probability here, i.e. why we don't need to model p of y equals 0 given x. And if you don't remember the answer, definitely go check out the lecture that was recorded for Monday. So again, we only need to model this single number here for binary classification. And of course, since we're talking about logistic models, we're going to actually be trying to figure out this number using a logistic classifier. And if I say logistic regression instead of logistic classifier, know that I'm talking about the same thing. These are just kind of two equivalent pieces of terminology that people like to use for these models. To actually write down sort of an expression for these logistic models, what they actually do, is that they are models of the following form. So I have some function z, which is a function of my feature vector x, as well as having some parameters theta. And this z of x given theta is just some linear combination of my weights and my features. So I take my weight theta naught, this is sometimes called like a bias term, and I add this to the sum over theta j times xj. So I just multiply my feature values times my weights in my parameter vector. This gives me some kind of unnormalized score, if you like. It's just some real valued number that is the output of this z function. But since we're modeling probabilities, we need to somehow take this unnormalized output and actually turn it into a valid probability score. So we need to take this unnormalized z and squash it down into the range 0, 1. And the way we achieve this is through this so-called sigmoid function, which is 1 plus 1 over e to the minus z. And we saw in the previous lecture, how this actually manages to achieve that transformation that we're interested in, i.e. mapping from unnormalized scores into probabilities. We'll sometimes use this notation p sub I as the output of our model on the ith data point. So p sub I is what I get by applying my logistic model to the ith data point in, say, a training data set. And this really is representing the model's belief or sort of the model's confidence in the probability that y equals 1 for this given data point. To actually learn these models, we sort of invented a new loss function in the previous lecture called the binary cross entropy loss. So this is this L sub BCE that I have here written on the slide. And what this really is it's a sum over all of my training data of the true label, y sub I, times the log probabilities. So by minimizing this binary cross entropy loss, what we're actually doing is maximizing the model's predicted probability for each of the correct classes in our data set. And here, note that we're sort of encoding the labels y as either zeros or ones. So when the true label is yi equals 1, this second term disappears, and we're only left with log pi, which again is the probability for the class y equals 1. So this gives me sort of the probability for the true label of this data point, and vice versa when yi is equal to 0. So again, make sure you refresh yourself on how we actually derived this loss function back in Monday's lecture. So in order to actually minimize this binary cross entropy loss function, we're going to be using this gradient descent algorithm that we saw in the regression module of this course. And just a refresher on how gradient descent works, we initialize our parameter vector as some random values, and we iteratively update this parameter vector with this equation here, where we take our current parameter values and step in the direction of the gradient of our loss function, where the sort of size of this step is controlled by the parameter lambda, corresponding to a step size, or sometimes called a learning rate. Here on the second line, I have an expression for the gradient of the binary cross entropy loss. We actually haven't derived this expression yet, but we'll see how to do that a little bit later in today's lecture. But take me at my word that this is the correct expression for the gradient here. And just a reminder of sort of the intuition that you should have in mind for gradient descent is that we initialize our parameters at some random value, kind of roll those parameters downhill, where the surface is representing the value of my loss. So I'm minimizing this loss by kind of moving downhill on my loss surface. So altogether, these two slides, this slide and the previous one, really summarize the whole logistic model in sort of a nutshell. So let's look at a couple of examples of logistic models and a couple of visualizations, just to give you guys more of an idea of what these models are kind of really doing to the data. So what I'm doing here is on the horizontal axis, I'm plotting my score function z, which again is my sort of linear combination of weights, theta, and features x. So again, it's not x on the x-axis here, it's z on the horizontal axis. And on the vertical axis, I have the corresponding predicted probabilities for the class y equals 1. So this is the output of my sigmoid function on the y-axis. What we saw previously is that as I make my score z very, very large, as z blows up to positive infinity, my predicted probability for the class y equals 1 goes to 1, and vice versa, as z gets very small, the predicted probability for class y equals 1 goes to 0. So you can think of the score function z as kind of encoding, sort of our score for how likely it is for the class to be y equals 1. So large values of the score mean it's very likely for our class to be y equals 1. We can actually turn these predicted probabilities into sort of hard decisions or class labels by predicting class y equals 1 if our score function is positive, or I guess in the top line here, we're predicting class 0 if our score function is negative, and we're predicting class 1 if our score function is positive. So again, this corresponds to a predicted probability of being more than 1/2 for class y equals 1 down here, and a predicted probability for class y equals 1 being less than 1/2 for the first line. In terms of sort of decision boundaries, our prediction regarding the label really flips when this predicted probability is equal to 1/2. So our model says it's equally likely that y equals 0 or that y equals 1. And of course, this is the point where we're not sure how to label our data point. Both of the labels are kind of equally likely, and so this forms our decision boundary. Rather than writing this in terms of the probabilities, which I did up here, you can also write this decision boundary in terms of sort of this underlying score function. And of course, this score function, when z is equal to 0, will give me a predicted probability of 0.5. Another way of thinking about logistic models that will be useful when we start talking about neural networks is as a sort of block diagram. And really, these block diagrams are showing you sort of the computations involved, sort of from start to finish, from data to output, of how these logistic models are making predictions. So on the very left-hand side of these block diagrams, I depict the inputs of my model. So these are the features, say x1, x2, and x3. And I additionally have a bias or an intercept term down here. And associated to each of my inputs, I have some corresponding weight, which are the parameters in my logistic model. In order to get my score function, this z function, I multiply each of the weights times each of the inputs, where here the weight theta naught is multiplied with my bias term because, again, this theta naught doesn't really get multiplied with the data. It's just sort of an additive constant. But I multiply all my weights times my inputs, sum them all up, and get this unnormalized score z. Then I pass this unnormalized score z through my logistic or sigmoid function. This is this 1 plus 1 over e to the minus z function. And then at the end of the day, I'll get my model output, which is a predicted probability for class y equals 1. And then if I want to, I can turn these predicted probabilities into hard predictions by doing this sort of thresholding step. So again, it's important that you guys sort of understand what this diagram is really depicting here. When we get to neural networks, we'll be drawing similar diagrams, but much more complicated. So understanding how these work for logistics models is a good step for building up to neural networks. Okay, let's look at a few examples of actually fitting logistic models on some toy made-up data sets. So here on my horizontal axis, I actually have now my feature value. So I'm doing a binary classification problem with only a single feature. And what we can see here is we have our decision boundary a little bit to the left of 0. So my decision boundary is maybe at, say, x equals 1. And what you should notice is that the predicted probabilities sort of smoothly interpolate between 0 and 1. If my predicted probability is close to 0 or close to 1, that means there's not a lot of uncertainty associated with that prediction. So for these data points down here on the left-hand side, and these data points at the top right, we're pretty confident what class we should predict for these data points because our data is fairly easy to separate in this example. All of my red points are sort of on the left-hand side, and almost all of my blue points are on the right-hand side. In the middle, though, sort of around this decision boundary, there is a little bit of uncertainty about what I should predict for these labels. Notice that for these blue dots here, my model is actually making incorrect predictions because these are on the left-hand side of my decision boundary. And so it's a good thing that the predicted probabilities, i.e. the values of this solid black curve, are not close to 0 or 1. We wouldn't want our model to be highly confident for these predictions because, well, it's incorrect for these. So again, we're somehow capturing the uncertainty in the model's predictions by looking at these probabilities. Here's another example where the data is much harder to separate. So my red points are now more spread out, and my blue points are also more sort of spread out here. What you should note is that the decision boundary for this data set is in exactly the same position it was in for the previous data set. But now, because there's so much overlap between my two classes, there should be a lot more uncertainty associated with my predictions. And in fact, there is, and that's sort of reflected in the fact that this probability curve, the solid black line, is not so sharp around the decision boundary. And there's a lot more uncertainty with regards to the model's predictions here. If we go in the other direction and make our two classes even easier to separate from one another, so it's a much easier classification problem, we see the opposite effect, where our predicted probability curve, the outputs of my model, becomes even steeper around the decision boundary. And this is good because our model can not only reflect sort of uncertainty, low confidence, but it can also reflect high confidence when it's sort of appropriate. We, of course, don't need to have our decision boundary right around x equals 0. So if our classes are, fairly easy to separate again, as in this example, but the decision boundary is a little bit shifted to the right, our data is maybe not centered, we didn't pre-process it for some reason, we, of course, with the logistic model can fit this kind of decision boundary. And another example, just showing you that these models are quite flexible and can do things that you would hope that they could do. If we sort of flip our classes around and put all of the blue classes on the left-hand side now, and all of the red classes on the right-hand side, we see that this predicted probability curve gets reflected and the model is actually able to accurately capture this data set. So again, in these sort of toy examples here, the idea is just illustrating what effects the data has on the learned logistic model. Okay, so in the last lecture, we briefly talked about decision boundaries and sort of how you get these. But here's a little bit more of a concrete example of how to actually calculate this decision boundary. So as we discussed previously, our decision boundary occurs when the two classes, y equals 0 and y equals 1, have equal predicted probabilities. And if you kind of back that out into an expression for the scores, we see that this is equivalent to seeing when the scores are equal to 0. And here I'm just writing out that expression for the score. It's just this linear combination. So let's do a slightly more concrete example. Let's say we have just two features in our data set, x sub 1 and x sub 2. To write down an equation for the decision boundary, then we set our score function, our linear combination, equal to 0. So any points, x sub 1 and x sub 2, any data points that satisfy this relationship, that the score is equal to 0, are going to be the points on my decision boundary. So for example, if theta naught, my bias term, is -4, theta 1 is 2, and theta 2 is 2, I get the expression x1 plus x2 is equal to 2. And of course, this is the equation for a line. If we solve for x2, we'll get x2 equals 2 minus x1. So this is a line with bias 2 and slope -1. So we get a really nice, fairly simple equation for the decision boundary. It's just a linear equation. Okay, let's visualize what that looks like. We maybe have, say, two classes here, our red classes and our blue classes. And this dashed line is the equation for this decision boundary that we just calculated. So I highly recommend that you guys know how to calculate these decision boundaries. If I give you, some weights, you'll be able to hopefully, draw an equation for this decision boundary. There's a homework problem on, drawing these decision boundaries, but yeah, make sure you know how to do this one by hand too. Let's look at another example of a logistic classification model. So what I've done here is I've taken a data set with two classes. These are my circle classes and my triangle classes. And the solid black line depicted here is that linear decision boundary that we sort of derived in the previous slide, corresponding to a predicted probability of 0.5. So this is just illustrating that, yeah, if we actually fit a logistic regression model on some real data, we do indeed get a linear decision boundary. And another thing here is I'm creating this sort of color plot where the colors depict the output probability values. And just as in the 1D examples that we had seen previously, there's sort of a smooth interpolation between probability values of 0 and probability values of 1. And again, we get a lot of uncertainty right around the decision boundary because these are data points where the model is, less confident. We're not so sure which label we should predict them as. Okay, let's look at another example of a 2D data set. So here we're going to fit a logistic regression model on a sort of toy synthetic data set with two features. One thing to note about this data set is that there is some overlap between my two classes. So some of these black dots are sort of occurring in the same region as a lot of these white dots. And so what we would hope to see in our model is sort of low confidences for the data points in this region, i.e. the probabilities that we predict for these types of data points in this overlap region should be closer to 1/2 than they are to either 0 or 1. And indeed, that's exactly what we see. So the blue line here is the linear decision boundary between the y equals 0 and the y equals 1 classes. And again, I'm using color here to represent predicted probabilities. And yeah, note that most of the probabilities near this decision boundary kind of fall in this range of something between 0.3 and 0.7 or something like this. Another way of visualizing these logistic models with two input features is in a sort of 3D plot. So on the sort of flat axes here, feature 1 and feature 2, I'm representing my actual input features. And on the vertical axis, I'm representing the output of my model. So we see a sort of smooth decision surface almost representing these predicted probabilities. And it's got this S-shaped sort of sigmoid shape that we had seen in the 1D example. So really, this is just to illustrate that you can think about logistic models in 2 dimensions and higher dimensions in a really similar way to those 1D examples I had shown before. So it's good intuition to keep in mind when you're thinking about what these models are doing. In this example, what I've done is I've taken my 2 classes that I had shown you previously, and I made them easier to separate. So there's less overlap now between the black dots and the white dots. And what we should hope to see, again, is that our model should be more confident about its predictions because there's less uncertainty associated with the labels near this decision boundary. And that's exactly what we see. There's sort of a sharper transition in the probability values right around this decision boundary. And again, in this 3D plot on the right-hand side, we see there's a much sort of steeper shape to this S-shaped curve. And again, going in the other extreme, if I have even more overlap between my 2 classes than in the first example, I should see my model be less confident about its predictions. There's a whole lot more uncertainty regarding which label I should predict in this region of overlap. So we should get a sort of decision surface, or sort of this probability surface should be a lot less steep than in the first example, and that's exactly what we see. Okay, so again, just to kind of put it all together, in logistic models, we have some kind of data, say, coming from 2 classes. And we can really think about our logistic regression classifier as either fitting a decision boundary, this linear boundary trying to separate our 2 classes, or we can also think about the sort of underlying probabilities coming from the model that represent uncertainty or represent model confidences. Okay, so really that kind of summarizes logistic models in, at least for the binary classification case. So in this next section, we're going to go through a fairly involved calculation on how you actually get gradients for these models. And of course, we need these gradients to do gradient descent. So we'll do that calculation now. Okay, so in pretty much most machine learning tasks, there's kind of general setup or paradigm for learning models. The first is we need to define our model. What's the functional form of our predictions? What does our sort of model look like? In our case, we're going to be using a logistic model here. The second thing we'll need is a loss function. So we're going to use the binary cross entropy loss that we've seen. Then we need to compute the gradients of this loss function, which we're going to do in just a second. And then lastly, we can apply those gradients in that gradient descent algorithm and minimize our loss from step 2. So really step 3 here is a crucial step, working out an expression for these gradients. And just a reminder of what a gradient is. So the gradient of a loss function L is a vector of partial derivatives of this loss function, where we have one component in this gradient per parameter. So for every parameter in our model, i.e. each of our weights theta naught up to theta d, we're computing the partial derivative of our loss with respect to that particular parameter. And again, partial derivatives are sort of like ordinary derivatives, where we're just seeing how does L change if I change, say, theta naught a little bit. So it's basically a derivative under the hood. So let's see to actually calculate each of these partial derivatives for the case of the binary cross entropy loss with a logistic model. Okay, so in the first line here, I just copied down my BCE loss. So this is just the loss function I'm trying to get the gradient for. And on the second line, what I'm doing is I'm taking the derivative of this LBCE with respect to the jth parameter in my model. So here J is going to eventually vary between 0 and D, but for now J is just some arbitrary subscript. What I can do is I can take this gradient, or sorry, this derivative, and pull it into my sum. For all intents and purposes, these yi's are constant with respect to the model weights theta. The true labels yi don't depend on what I have in my model, so they're constant with respect to this derivative. So I can sort of pull this inside a little bit. And of course, it also appears here. Now, using the rule for differentiating logarithms, which is the same rule as in sort of ordinary one variable calculus, and using the chain rule, I get the following expression for this derivative. So I'm differentiating, say, log f of x sub I with respect to theta j. This is 1 over f of x times the derivative of f. So this is the essentially the differentiation rule for logarithms right here. And then I'm doing the exact same thing for the second term in my summation as well. So yeah, just differentiating these log terms is what happened here. So what we see is that in order to actually calculate this expression on this line here, we need to be able to just calculate the derivative of f, my logistic model, with respect to theta j. And note that that same derivative appears here on this second term. So if I can calculate this derivative, I'm good to go. I can plug it into this line. So let's go ahead and do that. So the derivative of my logistic model with respect to theta j is, all I'm doing on this line is rewriting sort of the definition of f, where f is this sigmoid function applied to my score function. So z is that linear combination, that sort of almost linear regression looking thing that we then apply to the sigmoid function that changes the range of things to be between 0 and 1. Okay, recall that the sigmoid function is defined as follows. So sigma of z is 1 plus 1 over e to the minus c. This is our sort of squashing function. And you can use sort of standard ordinary calculus rules to show that the derivative of this sigmoid function is nothing but sigma of z times 1 minus sigma of z. So I really recommend and encourage you guys to, bust out your calculus and do this derivative. And you'll see that again, ordinary derivative of sigma z, you'll get this expression. But for now, you'll have to trust me that that's actually the correct answer. Then, knowing the derivative of sigma, we can use the chain rule. And so in doing so, we get that the derivative of sigma composed with the function z is just the derivative of sigma applied to z. So this is sigma of z times 1 minus sigma of z. This is that derivative we just showed on the previous slide. And then, of course, from the chain rule, we need to differentiate z with respect to theta j. So again, just the chain rule here. But since our z function is actually a linear function, it's just a linear combination of the weights and the parameters. So this is the expression for that z function right here. Well, if I differentiate this z function with respect to theta j, the only time theta j is appearing is against the xjth term. And so this derivative here is just going to be x sub ij. So there's a lot of equations on this slide, but all I'm doing at this point is gluing together everything we already showed. So the derivative of the BCE loss is, again, just pulling the derivative on the inside, using the log rule that we had done before. And now what I'm going to do is replace f of x sub I with p sub I. This is just another way of writing f of x sub I instead of writing it in f. I'm just writing it as the predicted probabilities. So just changing the notation and also plugging in that derivative calculation we had shown for this f function. You get this expression. And then from here, we just simplify things a little bit. So if you just kind of multiply everything out, expand, cancel stuff out, you'll get this line. One more step of simplifying, you'll get this final line down here. So a fairly ugly calculation, pretty involved, lots of symbols, lots of subscripts, things like that. But at the very end of the day, we get a relatively nice formula for the gradient, right? In order to get this derivative, all we have to do is sum over our n data points, look at the difference between the predicted probability for my model, so p sub I is the output of my model for the ith data point, compare that with the true label y sub I by subtracting them, and then we just multiply by our features x sub ij. Then we sum these again over the whole data set, and we've got our gradient. So it's pretty easy to implement this. You could do this in, maybe 1 or 2 lines of NumPy in order to actually get the gradients. Okay, so let's take a second to think about what's the time complexity of actually computing a gradient for this model. So in this first line, I have exactly the gradient that I wrote down on the previous slide. Instead of writing p sub I, I'm writing f of x sub I, but same exact thing, just different notation. But the first step in actually computing this gradient is essentially doing sort of a prediction with my model. So since I have n data points in my training data, and each of these sort of model predictions requires O of D calculations, it's a sum over D different terms, this total calculation here is going to be O of n sub D. And so subtracting off the yi's is another O of D calculation. So it's going to be O of nd overall. And really what you get out of this is a vector of length n. So for every one of my data points, having n of them, I'll get this difference between the predicted probability and the true label. The second step in calculating this gradient is that for each of my parameters j, so each of the weights in the model, I need to multiply each of these with the corresponding value of the jth feature in my data set. And then I need to sum these over my entire data set, going from I equals 1 to n. This again is an O of nd calculation, so you can pause for a second and think about why that is. But what this means is that overall, to compute our gradient, it's an O of n times d calculation. So it's linear in the size of the data set, as well as being linear in the number of parameters in my model. So overall, this is fairly cheap to compute, unless you have an absolutely massive data set. So unless you have a data set with like a million data points or even larger, this is something that's fairly cheap to compute. The most straightforward way to actually implement this gradient calculation, of course, is a for loop. So you could do a for loop to actually do this summation. Then you could do a for loop over the parameters to get each of these gradients. But really the easiest way and best way to do this is via vectorization. So hopefully you guys have gotten quite a bit of experience doing these vectorized calculations in the homework. So you can use functions like numpy.sum to actually do this summation instead of using a for loop. And also note you can parallelize this calculation in the sense that rather than computing this derivative for each theta sub j individually, you can compute them all in parallel by just putting everything into a sort of a big vector. So again, even if we do vectorization, the time complexity is still O of nd, but generally it'd be faster because each of these operations is going to be optimized a little bit. So we get O of nd time complexity for computing a single step of gradient descent. But of course, this is an iterative algorithm, and we usually take more than one step of gradient descent. So the overall time complexity is then O of nd times I, where, say, I is the total number of iterations until we pause our gradient descent algorithm, i.e. before convergence. We, of course, don't know sort of a priori how many iterations we're going to be using in our algorithm prior to convergence. Usually we stop our gradient descent algorithm when the gradient is, say, smaller than some threshold. So we don't know I in practice, but good to know that this just essentially scales linearly with the number of steps that we're doing. Okay, so as promised, we'll now get into some sort of additional topics about logistic models. So these are some sort of additional things that are nice to know. So one thing you can do with a logistic model is actually introduce some regularization. So we introduced the notion of regularization in a regression setting previously. So we saw how we can regularize linear models and how we can regularize, say, polynomial regression models. And just a reminder of how this works is that we start with sort of our usual loss function. In our case, it's going to be the binary cross entropy loss. And to that loss function, we add a new sort of penalty term, r of theta, where this function r of theta measures how complex our model is with the corresponding weights theta. So this is called the sort of regularization function. And again, high values of r of theta indicate very complex models, usually models that have large weights. And low values of r of theta indicate very simple models. And so by minimizing this new regularized loss function, we're forcing our model to kind of trade off between fitting the data very well and not having a too complicated of a model. And the idea is this helps us fight overfitting by preventing the model from being so complex that it can't generalize to new data. One of the benefits of logistic regression actually is that unlike KNN or near centroids that we had seen previously, we actually can regularize these models. Think back to a second to how KNN and near centroids work. How could you possibly regularize these things by adding a penalty term? So yeah, it's one of the nice benefits of logistic models is there's an explicit way to sort of control this overfitting phenomenon. So some examples of what you can actually use for the regularization function are, say, an L2 norm or an L1 norm of your model weights. So again, this is exactly what we saw for linear regression models, except we're now applying it into a classification setup. So all the same intuitions apply there. How do we actually set sort of this regularization weight? So again, we multiply our regularization function with some positive weight alpha, which is really representing sort of the strength of the regularization. So if alpha is 0, this corresponds, of course, to no regularization. This is just our standard logistic regression model. If we set alpha to be very large, then this has the effect of sort of upweighting the regularization term. So essentially, it's telling our model, yeah, I don't care how well you fit the data. I don't care how small or how large this binary cross entropy loss is. If I make alpha really, really big, I only care about the value of this regularization function. So in practice, what will happen is if you make alpha very, very large, well, the model is just going to set all the weights to 0 so that this regularization function goes to 0. And it's going to ignore this sort of binary cross entropy loss. Again, it's sort of upweighting the complexity term, which has the effect of downweighting the sort of classification term corresponding to this BCE loss. In practice, of course, alpha is some sort of hyperparameter of our model, and you'll need to tune this empirically, meaning you'll need to do lots of experiments on your data and just sort of pick which value of alpha works best for your particular data set. So you'll get some experience doing this in the second homework in problem 3. So just for the purposes of illustration, to show you what can happen, on the horizontal axis here, I have 1 over the regularization term. And I'm doing this because this is how scikit-learn decides to do it. We'll see an example of what it looks like in code in a second. But on the left-hand side of this, I have high regularization strength. And on the right-hand side of this, I have low regularization strength. So this is again 1 over alpha instead of alpha that I'm plotting. And on the vertical axis, I've got my accuracy of my trained models, and I'm also looking at the train set and the testing set. And what you can see is that for very low regularization strengths, I'm doing very good on my training data, very poorly on my testing data, and this indicates overfitting. But some point in the middle here is where I'm doing the best on my testing data, and you should always pick your parameters or your hyperparameters based on performance on your testing or your validation data. So here we should probably pick whatever value of alpha corresponds to this point here. Okay, so I'd like to take a brief aside here just to talk a little bit about the homework. So in particular, in homework 2, you're going to be working with this text data set called the Yelp data set. So I know you guys haven't really seen text data before, so I thought it would be helpful to go through this and just make it explicit how we're actually getting features out of text data and how we're actually sort of working with this type of data. So this Yelp data set is a text data set or a natural language data set consisting of Yelp reviews for a bunch of different businesses. And our goal is going to be essentially to classify these reviews as either a positive review or a negative review. So this is a task sometimes called sentiment analysis. We want to know, did this person like the restaurant they went to, or did they not like the restaurant they went to? So in the third discussion notebook, which is available on the Canvas page, there was a sort of short tutorial on working with this data. But again, just to really emphasize what's going on, here we've got some code that will load the data set for you. You're given this code in the homework and in the discussion notebook. And if we go ahead and print out the first data point in this Yelp dataset, we see that there's a whole bunch of sort of metadata associated with it, like review ID, user ID, business ID, so on and so forth. Then we've got this stars key, and the stars key is representing what this user of Yelp thought about this restaurant, or I guess hotel in this case. So they gave it 5 stars. This is a positive review. And then we've got some corresponding text associated with the review saying, my girlfriend and I stayed here for 3 nights and loved it, blah, blah, blah. And the goal, again, of this data set is somehow take the text of this data set and predict whether or not it was a positive review based on this text. So the way we turn this into a binary classification problem is that we are going to give a label y=1 for a particular review if stars is at least 4. So if they gave it at least 4 out of 5 stars, it's a positive review. And we're going to call it a negative review, i.e. label it as y=0 if stars is smaller than 2. In the case stars equals 3, I guess we call this a neutral review, and we're kind of throwing away these data points. So we're only looking at these 2 cases. We're turning them into binary labels. So again, you're given code to do this in the homework, but it's good to understand, what's really going on there. What we're going to do next is we're going to turn text, which is, again, just the text of the review, into actually a numerical feature vector that we can then plug into the algorithms we've been working at. And to do this, we're going to use a technique called bag of words. It's a very common technique in natural language processing. And in order to get a feature vector out of our text, our string of text, we're going to create a feature vector with length d, where the length of this feature vector is equal to the vocabulary size in our language. In practice, what we're going to do to reduce the number of features to make it manageable is our vocabulary size is going to be just the first 404 most common words in the English language. So if we have a word in our review that is not one of these most common words, we're just essentially going to discard it. Our feature vector then just counts how many times each of these words appears in the review. So let's look at an example of this. My first review might be, say, D1. It's the first row in this data set. And maybe the word great appears 3 times in this movie review. Or sorry, not movie review, but Yelp review. So we're just counting up how many times each of these words appeared in that text key. So we've essentially just got counts associated with the various words. So yeah, our features then are just essentially vocabulary words. And then we've got some associated class label, essentially whether or not this was a positive or a negative review. So hopefully it's clear from this how we're actually getting out sort of numerical representations of this text data. In terms of actually fitting logistic models in scikit-learn, as with any other machine learning problem, the input to a model to actually fit it is going to be our training data, which is this array having n rows, 1 row for every data point, and d columns, where d is, again, the number of vocabulary words we're considering for our bag of words representation. Then we also pass in the class labels. These are clearly necessary for us to fit our model, so we'll put those into the model as well. And the output of our model, after fitting things by minimizing our loss function, is going to be our d+1 real valued weights. So we have 1 weight essentially associated to every one of our vocabulary terms, plus an intercept term. So here's the doc page for scikit-learn. Definitely make sure you go ahead and read that. Make sure you understand how to actually use this. I will point out that with most scikit-learn functions, most scikit-learn models, you can actually fit these models using the .fit function, where you pass in your training data as X and the corresponding training labels as Y. There's also the predict function, which is going to go ahead and make sort of hard decisions from the model. So again, the logistic model predicts probabilities, but if you use this predict function, it'll take those predicted probabilities, threshold them, and use that to produce either zeros or ones. So actually predicting class labels. So a little bit of terminology that gets used in the scikit-learn documentation. N samples is the number of data points in our training data. So it's the number of rows in our data set. And features is the number of columns in our data, which in our case for the Yelp data set is going to be the size of our vocabulary. By a fitted estimator, we mean really the parameters specifying our model. So after we train a logistic model, sort of really what we get out of this procedure is some values for our weights, some values for our parameters, and these really define sort of the learned or the fit estimator. And sometimes instead of saying training or sort of learning a model, sometimes we'll call this fitting a model. So if you see that word, that's exactly what it means. It's to train or to learn our model. Okay, one thing I'd like to point out here is that the way scikit-learn does regularization is a little bit strange in my opinion. I'm not sure why they did it this way, but this penalty argument in the logistic regression class lets you specify the regularization function. So by default, it's using L2 regularization. It's the square of the weights essentially, but you could also use something like an L1 penalty if you'd like to play around with that. But the strange thing that they do here is that rather than passing in a regularization strength, which is what we've been working with in the slides, this sort of alpha variable that I introduced, they actually use the inverse regularization strength. So C is equal to 1 over alpha, where alpha is that strength we had shown in a few slides ago. So yeah, just to note that small values of C are going to represent large values of alpha and vice versa. So the last thing I'd like to introduce here is that you can actually sort of interpret the weights of a logistic regression model, and in doing so, get some insight about your data set. So again, just a reminder that we can think about logistic models as taking in some score function z and producing some predicted probability based on those scores. And the decision boundary, again, is when this predicted probability is 1/2. And something we'd like to ask ourselves is, well, since this score z is really determining the predicted probability, can we kind of crack open our model and inspect the weights and tell us which of these weights has, sort of a large impact on the value of z? Maybe there's some weights that really tell us how large or how small z is going to be. And then perhaps interpreting those weights can tell us something about our data set or can tell us something interesting about our model. And in fact, we can do that as follows. So let's assume, just to make things simple, that all of our features are non-negative. So all of our x's are positive values. Now imagine for a second that we fix all of our features for some data point, except for the very first feature, x sub 1. And if we increase x sub 1, so we make this first feature larger, if the corresponding weight in our logistic model, theta sub 1, is large, this is going to have the effect of increasing that score z. And also, the larger that theta is, sort of the faster z increases. In contrast, if theta 1 is negative and x1 increases, then this is going to decrease the value of z. So again, this is just basically inspecting sort of the form of z. It's this linear combination of weights and features. So again, positive weights increases z, negative weights decreases z. Sort of the magnitude of that parameter theta tells you how fast this increase or decrease is happening. And if a weight is 0 in our model, then what this really means is that changing x1 has no effect on this z value, and in effect, the classifier is ignoring x1. So if a corresponding weight is 0 or is very small, then the classifier has kind of learned that this feature is not relevant for the prediction it's trying to make. So really, we can interpret the weights in our model sort of in two complementary ways. The sign of our weight, either positive or negative, tells us how increasing x1 changes the predicted probability. And then we can also look at the magnitude of this corresponding weight. And this really tells us sort of how much changing this feature affects the corresponding prediction. So the sign tells you kind of the direction of the effect, and the magnitude tells you sort of the strength of the effect. So let's look at an example of sort of what some of these weights look like on the Yelp dataset. So I fit a logistic model to this Yelp dataset It's using slightly different data than the data you'll use in homework too, so you should expect to get slightly different answers when you do this problem yourself. But if I look at the largest weights in my model, and I also make sure that they are the largest positive weights, I see that they're associated with words, i.e. features, that we should really think of as having positive sentiment. So things like pleased, excellent, amazing, so on and so forth, these get very positive weights in my logistic model. What this means is that if I see a review that has the word pleased appearing in it frequently and excellent appearing in it frequently, my model is going to be much more likely to predict that it's a positive review. In contrast, if I look at the smallest weights in the sense of being the largest negative weights, I see words like worst, horrible, soggy, so on and so forth. So, okay, soggy, that's a bit of a strange one. I forgot that one was in there. Caught me a little off guard. But yeah, essentially, if these words are appearing in my movie review, then it's going to decrease the positive sentiment that the model is predicting. So if worst appears, my model is going to be much more likely to classify that data point as a negative movie review. Okay, so there's some more content here we'll cover in Friday's lecture, but let's just really briefly wrap up. So maybe or not, because I seem to have lost my slides, but I'll see you guys in Friday's lecture for the final remote lecture, and we'll start talking about neural networks then. So see you all guys then.